Hey everyone, let's jump right into this explainer and get you completely prepped and, more importantly, totally confident for your fluid mechanics exam. I'm stepping into my absolute favorite role today as your personal physics tutor. We're going to take all those dense, kind of intimidating formulas from your textbook and break them down into clear, visual, and super memorable concepts. So, if you've been struggling with pressure, flow, or viscosity, just take a deep breath. By the end of this session, you're going to have a rock-solid grasp of the mechanical properties of fluids.
Here is our exact blueprint for this review session. We're covering fluid basics, fluid statics, fluid dynamics, real-world forces, boundary interactions, and we'll wrap it all up with a quick flashcard review. Let's get right to it.
All right, Section 1, Fluid Basics.
Now, what's really interesting here is that the defining property of fluids is actually how they respond to shear stress. Think about pushing a solid block of wood from the side. It pushes back, right? It has a really high resistance to that sliding, shearing force. But fluids, meaning both liquids and gases, offer almost zero resistance compared to solids. In fact, a fluid's shearing stress is about 1,000,000 times smaller than a solid's. It just yields. It flows. And that right there is your core definition. A fluid is literally a substance that flows continuously under shear stress.
Next up, we have your two fundamental variables. When we're dealing with fluids, we honestly rarely talk about total mass or total force. Instead, we use density and pressure. Density is simply mass divided by volume. The key takeaway for your exam, liquid density is practically constant. It's incompressible. Gas density, on the other hand, varies wildly depending on its environment. Then we have pressure. This is just force distributed normally or perpendicularly over an area, measured in pascals. Just remember, pressure is a scalar quantity. It acts in all directions, but the actual force it exerts on a surface is always strictly 90 degrees to that surface.
Moving right along to Section 2, Fluid Statics, under pressure. For calculating pressure at depth, your formula translates to plain English like this. Total pressure equals the atmospheric baseline plus the literal weight of the fluid column directly above you. That second part, the fluid's weight, is calculated as density times gravity times depth, or ρgh. And here is a totally crucial insight. Because a liquid's density is constant, the pressure difference between any 2 points in the water depends strictly on the vertical distance between them. The shape of the container doesn't matter at all. A wide lake and a narrow pipe that are the exact same depth will have the exact same pressure at the bottom. Okay, stop right here. Tutor warning, the absolute most common pitfall on exams is calculating only the gauge pressure, that ρgh part, and forgetting entirely to add the atmospheric baseline on top. If a question asks you for the absolute or total pressure at the bottom of a pool, you absolutely must add that 1.013 times 10 to the 5th pascals of atmospheric pressure that's pressing down on the surface. Write that down in big, bold letters in your notes right now. And this brings us to a massive 17th century breakthrough by the scientist Blaise Pascal. Because pressure is transmitted equally everywhere in a resting fluid, Pascal's law shows us how multiplying the container's area proportionally multiplies your force. Think of it like a multiplier cheat code. You apply a tiny force to a small piston, which creates a specific pressure. That exact same pressure travels completely undiminished through the fluid to a larger piston. If the second piston has an area 50 times larger, guess what? Your upward force just became 50 times larger. That is literally how a standard hydraulic lift can effortlessly hoist a massive car into the air with just a tiny input force. All right, Section 3, Fluid Dynamics, Steady Flow. Let's get these fluids moving. Before you even think about applying any dynamic equations on your test, you've got to determine the flow type. Are you dealing with nice, neat, streamlined laminar flow or chaotic, turbulent flow? Streamlined flow happens below a certain critical speed. The velocity of every passing particle stays perfectly constant over time, and their paths never, ever intersect. But the second a fluid exceeds that critical speed or hits a major obstacle, it devolves into turbulent flow, where velocity and pressure are just wildly fluctuating. To really visualize this, think of laminar flow like cars cruising smoothly in their own lanes on an open highway. Everyone stays in their lane, everything moves predictably. Turbulent flow, on the other hand, is a chaotic, gridlocked traffic jam. Cars are weaving, braking abruptly, causing a total mess. And just like a traffic jam wastes gas, turbulent flow is incredibly inefficient because massive amounts of kinetic energy are rapidly lost to internal friction and chaotic swirling eddies. Now, most of your introductory exam problems will assume laminar flow, but you definitely need to know the difference.
So here is my go-to reliable 3-step problem-solving hack for your exam. Step 1. Always scan your word problems for the word incompressible, which usually just means you're dealing with a liquid. Step 2. Check if it says ideal fluid or zero viscosity, which tells us we can completely ignore friction. Once you've confirmed those 2 conditions, step 3. You can safely pull out your dynamic equation toolkit, starting with our next 2 heavy hitters. If the fluid is incompressible, the equation of continuity dictates that mass is strictly conserved. The math is beautifully simple. Area 1 times velocity 1 equals area 2 times velocity 2. A1 V1 equals A2 V2. It basically means what goes in absolutely must come out. Think about putting your thumb over the end of a garden hose. You decrease the area, right? So what happens? The water shoots out way faster. Wherever the pipe narrows, the fluid has to accelerate. Area and velocity are strictly inversely proportional. And this perfectly illustrates our next major timeline milestone, the incredible 18th century breakthrough known as Bernoulli's principle. In a steady, ideal flow without viscosity, the sum total of pressure energy, kinetic energy, and potential energy remains completely constant. It is essentially the law of conservation of energy applied directly to fluids. Think of it like a strict energy budget. If a fluid flows through a level pipe and speeds up, meaning its kinetic energy spikes, that energy has to be borrowed from somewhere else. The budget dictates that the pressure energy must drop to compensate. Faster-moving fluids exert less pressure. Pretty wild, right? A classic real-world application of this exact energy conservation is dynamic lift. Just picture the cross-section of an airplane wing. Because of the specific shape and angle, the air flowing over the top literally travels faster than the air flowing underneath. Higher velocity means lower pressure on top. Lower velocity means higher pressure on the bottom. Amazingly, a mere 8% speed difference between the top and bottom of a commercial wing generates enough massive lift force to keep tons of heavy metal suspended in the sky.
Section 4. Real-world forces, viscosity. Let's talk about friction.
So, viscosity is basically the internal friction of the flow. In the real world, fluid layers drag against each other, and they drag against the walls of their container. In fact, the fluid directly touching a pipe wall is literally stationary. The velocity only increases as you move toward the center of the flow. We measure this friction using the coefficient of viscosity. And here is a super surprising fact for you. Human blood is technically thicker than water, and it maintains remarkably constant relative viscosity anywhere between 0 and 37 degrees Celsius. That specific quirk is absolutely vital for keeping our cardiovascular systems healthy across wildly different environments. Moving right into the 19th century of fluid mechanics, we find that when objects fall through these viscous fluids, Stokes' law takes the stage. It proves that viscous drag is proportional to the object's velocity, the fluid's viscosity, and the radius of the sphere. Imagine a raindrop accelerating toward Earth. As it speeds up, the upward viscous drag increases right along with it. Eventually, that upward drag force, combined with buoyancy, perfectly balances out the downward force of gravity. Net force hits 0, acceleration completely stops, and the raindrop falls at a constant, totally safe terminal velocity. Without Stokes' law, a simple, everyday rainstorm would be lethal.
Section 5. Boundary interactions. Let's zoom way into the microscopic level.
Deep inside a liquid, a molecule is being pulled equally in every single direction by its neighbors. But the molecules right on the surface, they experience unbalanced, entirely inward forces. This creates a tight state of tension and extra potential energy, acting exactly like a stretched elastic boundary. Because systems in nature are lazy and always try to minimize their potential energy, liquids naturally configure themselves to minimize surface area. That's exactly why free-falling raindrops and floating soap bubbles naturally form into perfect spheres, because geometrically, a sphere has the smallest possible surface area for any given volume. Now, depending on whether adhesive or cohesive forces win the tug-of-war, fluids interact really differently with solid boundaries. If water-to-water cohesive forces are stronger, the fluid refuses to spread out. It forms a little bead, which we call non-wetting. But if the water-to-solid adhesive forces are stronger, the fluid sticks and spreads out, wetting the surface. And this wetting property is the direct driver of capillary action. When you have an acute contact angle, a pressure deficit forms just below the surface meniscus. This acts like a tiny upward vacuum, literally pulling water upwards to defy gravity. Actually, that's exactly how giant redwood trees manage to pull water hundreds of feet straight up from their roots. So,
The grand takeaway here is how all these distinct laws integrate into one giant, interconnected global fluid ecosystem that dictates the physical architecture of our world. Next time you picture an airplane flying through a storm, remember, Bernoulli's principle is generating the lift, Pascal's law is powering the enclosed hydraulic landing gear, Stokes' law is governing the terminal velocity of the rain smacking the windshield, and surface tension is at play in the turbulent wind shear. It all connects seamlessly.
All right, section 6, pencils down. Let's lock this in with a quick flashcard review.
Let's do a rapid-fire summary to ensure you're 100% test ready. Keep these 5 golden rules locked in your brain. 1. Fluids yield and flow freely under shear stress. 2. Total pressure must always include the atmospheric baseline. 3. The continuity equation means fluid speed increases when pipes narrow. 4. Bernoulli's principle is just total energy conservation in flow. And 5. Stokes' law explains why viscous drag creates a safe terminal velocity. You've got this for sure, but I'll leave you with this final, somewhat provocative thought to ponder before your exam. If extreme global temperatures were to suddenly change the fundamental density of a fluid overnight, which of these physical ecosystem rules do you think would break down first? Think about it, study hard, and I'll catch you in the next explainer.